Okay, hello everyone. Welcome to tonight's webinar about the impacts of contaminants on Nebraska's water. My name is Kristen Jansen, and I am an AmeriCorps member serving with Conservation Nebraska's Common Ground program. Conservation Nebraska's mission is to protect our state's natural legacy by educating the public, supporting communities, and increasing civic engagement, which we accomplish through locally led education efforts and community engagement projects to address local conservation concerns. Before tonight's speaker, there's just a few housekeeping things to go over. Your cameras will remain off and you will be muted throughout the presentation. So please type any questions that you have in the chat or the question and answer section, and we will answer those at some point today. Following the presentation, we will have a very brief survey that should only take less than a minute to complete. The survey helps support programming like this one, so we appreciate you taking the time to fill this out. If anyone in attendance is interested in speaking with a member of Conservation Nebraska about what we do or to get any information, I will put our contact information in the chat. We also have a water testing kits that we are going to be sending out. I will post the link in the chat if you're interested in getting a kit sent to you. If you're on a private well, then you can test those and you can see if you need to treat your water. We have with us tonight Dan Snow, and he's going to be talking about how contaminants impact Nebraska's water. So I will just go ahead and let him take it away.
Like there's a question in the chat.
Yes, we will. We're recording this and then it will be uploaded to our YouTube page in a couple of weeks, and we will send out an email with some more information about how you can access that after this.
I'm going to share my screen first to make sure it's accessible. Can everybody see that?
I can see it on my end.
Okay, great. Well, thanks everyone. Really enjoy being able to talk about something that I'm pretty excited about, talking about water quality. I am a research professor in the University of Nebraska School of Natural Resources and director of the Water Sciences Laboratory, part of the Nebraska Water Center at the university. My background, I grew up on a farm in southwest Iowa, went off and got degrees in geology and geochemistry, and then pretty much stayed and had my whole career here in Nebraska, learning and studying about water quality and water resources issues. So I'm really excited to be talking about water quality tonight. Here's just an overview of the things that I plan to talk about, really just a general overview about what water quality is. Just want to mention the Safe Drinking Water Act, how it came to be. Talk about nitrate in groundwater, the Nebraska nitrate report. Then a little bit about geogenic contaminants, which you may or may not have heard about. And then round it up with a little bit about our Know Your Well citizen science program. So the first question I ask a lot of students, I used to teach water quality. What is quality? What is water quality? Well, really for water, it's a measure of the suitability of water for a particular use. You might look at that waterfall in Cherry County, Nebraska, Smith Falls. Maybe some of you have been to it and wonder, well, is that water safe for drinking? Is it safe for swimming in or getting a cold head? Is it something that you might find fish in? You know, the water that spills out into the stream and eventually into the Niobrara River. Those are all questions that you can answer basically by evaluating its quality. And we basically define water quality based on physical, chemical, and biological characteristics. Typically, we're looking for specific contaminants or characteristics. We make measurements and we compare those measurements to standards and guidelines. basically to ensure that water is safe for its intended purpose. So a little bit about the Safe Drinking Water Act. In the 1960s, when I was a kid, 1969, I was 10 years old. There was a survey conducted of U.S. Public drinking water systems, and they found that only 60%, barely half, met minimum health standards. And this is public water systems. And I imagine that quite a few of you are consumers of public drinking water. So when you can only count on about half of those city systems to provide safe drinking water act, minimum health standards, then you know that maybe we should be doing something to improve that quality. And about the same time, 1970, the Environmental Protection Agency was created. That was followed up shortly thereafter by a study in 1972 that found 36 chemicals in treated municipal drinking water from the Mississippi River. And I actually got my master's degree in Baton Rouge, Louisiana, not very far from New Orleans. Turns out that in New Orleans, the city of New Orleans was using treated Mississippi River water, and they found 36 contaminants that were toxic, really not suitable for human consumption in that treated drinking water. So that led to, and many other activities and studies led to the creation of the Safe Drinking Water Act in 1974, which allowed the EPA to regulate the quality of public drinking water supplies. And I want to stress that this is for public drinking water. The vast majority of U.S. citizens consume water from public supplies, but there's actually quite a few people that have their own wells. And that's what a good part of my talk is going to be about, is water quality in these private wells. So where are those standards that we measure and compare to for drinking water under the Safe Drinking Water Act? Well, the regulated contaminants for public water systems include 16 inorganic contaminants, which includes nitrate and nitrite, 55 organic contaminants, which includes many pesticides, and a good number of those organic contaminants that were found in the New Orleans drinking water supply, 4 radioactive contaminants, 7 microbiological, like E. coli is one of the, and total coliforms are 2 of the microbiological contaminants that they measure in public water systems, as well as 7 disinfectants and DBPs, or disinfection byproducts, that are known to cause human health effects. And the concentrations are set at levels that would minimize health effects to humans from long-term chronic low-level exposure. That is, if you're drinking this source of tap water every day, we're going to estimate how much exposure you're going to get by drinking this tap water over the long term. And really, most public water supplies in the United States have a very low probability of a maximum contaminant level violation, that MCL violation, which is a Safe Drinking Water Act set standard to protect consumers of public water from the health effects of contaminants. So when I go and give talks in other countries, I talk about what great water we have. It's not the best in the world, but it's definitely among the top 10%. Our system of drawing and delivering water through cities and towns in the U.S. is among the best in the world. So I'm sure many of you have heard about nitrate in Nebraska groundwater. Nitrate is one of the contaminants that's regulated under the Safe Drinking Water Act. And I'm going to talk a little bit about nitrate and kind of what concentrations we find in Nebraska's groundwater. These are just a couple of news articles that occurred earlier this year about the nitrate issue in Nebraska's groundwater. So it's really been in the public eye quite a bit recently. So what is that nitrate, maximum contaminant level, or MCL? It's set low enough to protect infants from a condition called methemoglobinemia, or blue baby syndrome. What happens when an infant consumes high levels of nitrate in their formula, they can that nitrate gets reduced to nitrite, and that nitrite actually binds with the blood hemoglobin and interferes with oxygen uptake in the blood. And that's why they call it blue baby syndrome. Is an infant that's consuming high nitrate water will develop a bluish skin color because of the lack of oxygen in their blood. There's also a possible association between chronic nitrate exposure during pregnancy and human birth defects or malformations. There's some evidence for teratogenic effects attributed to nitrate and nitrite ingestion. I think the bladder cancer is one of the associated human health effects from nitrate consumption, and association between nitrate or nitrite exposure and cancer is conflicting. And I think that's just because we haven't done enough work on coming up with these connections between long-term consumption of high nitrate water and human health effects. So where does nitrate come from? Well, here is a cartoon or diagram of the nitrogen cycle, and it shows many of the pathways that could lead to nitrate contamination in groundwater. That red arrow that's pointing down indicates that if we have excess nitrate, which is just a form of nitrogen, anywhere in that soil or the subsoil just above the groundwater, we have the potential risk of leaching nitrate into groundwater. So that nitrate can come from nitrification of organic nitrogen in the soil. That organic nitrogen can come about because of biological fixation in bacteria and root nodules and legume crops. But for the most part, in agricultural systems, most of that nitrogen comes from excess fertilizer application. We use a lot of fertilizer in Nebraska to raise corn, a little bit less using for soybeans and other crops. But because we use so much fertilizer and because much of that cropland is irrigated, some of that nitrate that's produced in soil gets leached below the root zone and eventually to the water table. I think you probably have noticed, though, that there's quite a bit of variability or complexity to the nitrogen cycle. We can get nitrogen from the atmosphere. We can have ammonia that's excreted from livestock. We can also have nitrate from septic systems that occur in the soil and vadose and may eventually get to the groundwater. But here in the Midwest, where we have a lot of agriculture, for the most part, our excess nitrogen comes from either one of two forms: nitrate from excess fertilization, or from excess nitrogen from over application of manure. So why does it end up in groundwater? Well, here's a diagram of the hydrologic cycle, basically showing how close the water table is in comparison to our cropland and our surface soils. And I added a little structure next to the trees. See if I can point it out. So what happens if we have a house with a well, and that well is in the shallow part of the water table, and we're applying fertilizer uphill, right, on this crop, and some of that fertilizer leaches below the root zone and gets into the groundwater. A lot of it, or a good portion of it, could intercept with that domestic well. And we'll talk in just a little bit about how domestic wells are particularly vulnerable to contamination. We can actually have excess nitrogen from from cropland that gets into our streams. This diagram also shows how groundwater can re-enter streams if we go further downhill. So we have many streams in Nebraska, mostly in the eastern part of the state, that end up becoming enriched high in nitrate concentrations by this mechanism. So there's been a lot of work done in the past several decades on nitrate in groundwater. Our U.S. Geological Survey has published a lot of reports for the United States. This is one that was published not quite 10 years ago, looking at the quality of groundwater in the United States. And they were trying to predict concentrations of nitrate in shallow, recently recharged groundwater, similar to what I was showing in that hydrologic diagram. And even in deeper groundwater that's used for drinking water, primarily for public water systems. And those areas in orange and red are those that are predicted to have concentrations higher than background. And what this study found was that based on a model, basically this is a model that predicted the amount of nitrate that could leach below the root zone. More than 30% of the U.S. drinking water wells, public and private, would have high nitrate concentrations. And you might notice from the map, Nebraska, right in the center of the United States, has quite a bit of red and orange, indicating that we have, unfortunately, we have a lot of area of the state with high nitrate. So what are some factors that lead to high nitrate in groundwater? Well, in Nebraska, we have very sandy soils, low water holding capacity, and at the same time, we have a lot of irrigation wells. So we're irrigating a lot of cropland, and when we add more water in excess of what the crop can use to sandy soils with low water holding capacity, that can actually cause flushing of nitrate below the root zone. If you couple that with a shallow water table, in that diagram that I showed earlier, you have a really short distance to the water table, and that nitrate can be very rapidly leached to the water table. That thin vadose zone, or the unsaturated zone, really those red areas in the state that are shown in this particular map, where we see higher and higher nitrate concentrations. All four of those factors contribute to high nitrate in groundwater. So this is another way to look at groundwater or nitrate in Nebraska's groundwater. Here's important aquifers and topographic regions of the state. The topographic regions with the green hatch lines, those are the river valleys. And the one that runs all the way from the western part of the state to just before the Missouri River is actually the Platte River alluvial valley. And that river valley is one that has high nitrate. So if we do an overview map of the median groundwater nitrate we see that the red actually shows up pretty prominently in those river valleys. That's because the soils are very sandy. We have a lot of irrigation, irrigated cropland, and we tend to flush nitrate to the water table through crop production. So we've been studying nitrate in groundwater for almost as long as I've been in Nebraska. I came to Nebraska to do my doctorate in 1986. So there were some studies that were published in the 1970s on high nitrate in the Central Platte. Those are the areas in red, the Central Platte Natural Resources District, right along the Platte River Valley. If we look at irrigation wells, we see even more high nitrate. Really, the only difference between this map and the previous one is these are drinking water wells, domestic and public water wells from the Nebraska Clearinghouse. So now shows you really kind of the extent of groundwater nitrate that we've measured in all of these wells. So roughly 60,500 samples. from almost 3,000 wells that were collected between 2000 and 2019. Just this year, the state did a predictive nitrate model, basically using a bunch of water samples that they collected last year, put all that data into a database along with a clearinghouse database. And then they came up with a model that helped to predict, very much like the USGS maps predicted, where we might see higher nitrate levels in groundwater throughout the state. And what you can see is there's actually even more areas of the state where we might have to start looking for high nitrate in our groundwater. So we're really getting closer and closer to a more accurate picture of how much of the state has high nitrate. Really, we want to couple this model with more samples from areas that we have very few samples collected or not very recent samples collected. And then we want to put that into our database so that our model gets more and more accurate over time. So it's not just nitrate. I mentioned in my outline that I wanted to talk a little bit about geogenic contaminants. And I did my PhD work on uranium geochemistry in Nebraska. I learned during that work that we have a lot of areas in the state that are high in uranium concentration. And uranium is one of those geogenic contaminants that we talk about. And yet sometimes you will see in a municipal public water system water quality report. The map on the lower left-hand side shows the public water systems that had violations or were treating for high nitrate or high uranium. We had the triangle show all of the systems that are treating for uranium, basically to treat the raw water and reduce uranium. They might have had an administrative order, which means they've had an exceedance of the uranium maximum contaminant level. And then for comparison, we can see that how these systems compare to our topographic regions. And you might notice that many of these areas for uranium actually co-occur with that high nitrate. And that was something that we've been really looking hard more frequently into, is the co-association of high nitrate with some of these geogenic contaminants like uranium. So on the right-hand side, we've got arsenic concentrations. Arsenic is another one that we've had quite a few not MCL violations or systems that are treating for high arsenic levels. Arsenic doesn't quite follow the same model as uranium does, but nevertheless, we do see some association with areas where we have nitrate contamination and with arsenic. And the thing about these geogenic contaminants is they are not monitored nearly as frequently as nitrate and bacteria. So one of the projects that I'm working on is trying to change that, where we are getting domestic wells tested more frequently for some of these geogenic contaminants. So where do these geogenic contaminants come from? It's really kind of complicated. It's a lot harder to understand, I think, in comparison to nitrate. But this diagram actually shows a good part of what we think is happening. Is that we think when we apply water and an oxidizing agent like nitrate at the surface, that water and nitrate and perhaps bicarbonate can actually accelerate weathering in the sediments. And that can start to erode or chemically weather the sediments that are naturally high in some of these contaminants. They can go from a zone where there's high oxygen levels into zones where there's low oxygen levels. And that change from high to low oxygen it can control what we call redox chemistry. That redox chemistry can actually cause, it can redissolve these metals or these geogenic contaminants from the sediments that are naturally occurring in the sediments. In Nebraska, we have naturally high soil and sediment levels of uranium, result of weathering from the Rocky Mountains and being redeposited here in the Great Plains. So it's not just Nebraska. There's places in Kansas that has issues with high uranium levels. They all were originally derived from the really high uranium igneous rocks in the Rocky Mountains. So this is from a study that was published just about 2 years ago or 3 years ago, indicated that uranium is an unappreciated contaminant in U.S. community water systems. And I was actually quite happy to see that, because I have suspected for a very long time that uranium and some of these other geogenic contaminants is something that really deserve a lot more study and understanding and monitoring, basically to help protect human health. You can see in the center of the map that there's quite a few counties that have high elevated concentrations of uranium. And I recall from the research that I did in the Central Platte, there was actually some that were about 10 times higher than the 30 microgram per liter maximum contaminant level, over 300 parts per billion uranium in some of the samples that we collected. So it's definitely something that we need to pay attention to. And if there's high uranium in a domestic well, that take some precautions to treat that water with an appropriate treatment system. So I promised to talk a little bit more about private and domestic wells. I really want to stress that domestic wells are quite a bit different than public supply wells. And that's what this diagram and the illustration show. Number one, private domestic wells are not regulated under the Safe Drinking Water Act. That is, they are totally under the purview of the well owner or the water user of that well. There's no requirement to have that well tested, except in some places where you're selling a house. Very often there is actually no requirement to have a well tested. So it's all voluntary for the most part, unless you sell the property. The domestic wells is shown on this diagram, this hydrologic diagram, generally pretty shallow in comparison to monitoring wells or public supply wells. And for that reason, they're also quite vulnerable to any contaminants that might originate from the surface. These nitrate, as I showed in an earlier diagram, is just basically being leached from the surface soils down to the water table. If we're also leaching some of these geogenic contaminants, and in some small number of cases, maybe some pesticide residues in the soil, then those could add to issues affecting the quality of that domestic well water. And domestic wells are only treated or tested voluntarily. They're not tested very often. In many cases, there's not much treatment that's done. So we really want to get the word out that these domestic wells need to be tested. And if they're found to contain contaminants above what we consider to be safe, that the owner should look into some sort of a treatment. So how many people are using domestic wells? Well, this map shows the density of people using domestic supply wells in the United States. You can see that there's actually quite high densities out east and in Michigan and Minnesota. Here in Nebraska, we have around 145,000 domestic wells. Maybe a fourth of those or less than a fourth are registered and have been tested. So there's quite a few that are not registered and that have not been, to our knowledge, has not been tested. So what do we know about domestic well quality? This is a study that was published by the U.S. Geological Survey looking at the quality of water from domestic wells in a variety of aquifers across the U.S. We looked at a whole range of different contaminants, and I'm not going to go through all of them, just try to quickly summarize those. You can see Nebraska in the center of the U.S. had quite a few blue dots from the sand and gravel aquifers, many of which are very close to the surface along the Platte River alluvial aquifer and some of our other aquifer systems. So the summary that they provided here actually gives us a pretty good snapshot of rural domestic wells across the U.S., including Nebraska. So what did they find? Roughly 23% of the wells sampled contained one or more contaminants higher than the MCL or maximum contaminant level. Or if it didn't have an MCL, it had a concentration higher than the health benchmark safe level. So we don't regulate for all contaminants, but in the cases of those that weren't regulated, they also compared it to a standard that they called the health benchmark. What they found was that inorganic contaminants, including nitrate, tended to occur more frequently than those organic contaminants like pesticides and solvents. And nitrate levels were greater than the human health benchmarks in about 4.5% of the wells sampled across the US. So nitrate was one of those that occurred most frequently at concentrations that we should probably treat for. E. coli and total coliforms were detected in 34% of the wells tested. E. coli is a human pathogen or can be a human pathogen, whereas total coliforms are not harmful, but they can be an indicator that that well probably needs to be disinfected. Almost half of the wells contain at least one contaminant outside the range recommended for aesthetic quality. That is, the water was very hard. It tend to produce iron or manganese stains, and it had an unpleasant odor or taste. And in general, contaminants tended to co-occur. That is, nitrate tended to co-occur with diethylatrazine, which is a herbicide degradation product, or nitrate occurred in samples with high radon levels. And many people don't realize that radon can actually occur in groundwater, and if you're pumping that groundwater directly into your house, that might be another route where you could actually increase radon levels. Radon is a gas, a radioactive gas that many households have to remediate from their basements. So what this tells us is that domestic wells definitely deserve more attention, and that we tend to see mixtures of contaminants at concentrations that are above what we consider to be safe. So the top 8 inorganic contaminants include radon. Strontium is another one that occurred at concentrations above what we might consider to be safe. Arsenic is one of those that we have in Nebraska. Manganese is typically considered to be a nuisance contaminant, although there's some studies underway now that maybe are finding some human health effects associated with manganese exposure. Nitrate, as well as uranium, boron, and fluoride. Those top 8 inorganic contaminants, number of wells that were sampled, and frequency of detection are all shown in this table from that USGS report. So arsenic is, we just had a talk on arsenic at our water resources seminar last week. Arsenic is becoming much more visible in the public eye, not just in the US, but across the globe. Here's that probability of arsenic that was published I believe by the US Geological Survey based on a number of different factors. But we can see that Nebraska has a good portion of the state where we have a high probability of arsenic in our groundwater, and that definitely deserves some more attention. We don't have the highest for the US. It looks like, based on this map, that Nevada, Utah, New Mexico, Arizona probably have the highest levels, although Maine seems to be pretty high as another area where you'd expect to see high arsenic in the groundwater. So the last thing I wanted to talk about was our Know Your Well program. This is something that started back in 2017. We're getting high school groups to learn about domestic well water quality and go out and actually collect and test wells. They send us split samples that are properly collected and preserved to the Water Sciences Laboratory, and then we send those results back to them and to the well owner, so they get a pretty comprehensive analysis of the well water quality. Our long-term plan is to develop a curriculum for teachers. Actually, that curriculum is being tested right now. And hopefully we can get more of these Know Your Well high school groups out there sampling and testing domestic wells in their communities. So here's just a quick rundown on the Know Your Well program. Students screen samples using test probes and visual comparison kits or portable colorimeters. They'll measure things like pH, temperature, conductivity, total coliform and E. coli using a ColAlert kit. They measure nitrate using a test kit like that one I showed in the slides. And then they have colorimetric kits for iron, copper, and manganese. We originally started with an atrazine test strip, but that test strip was discontinued. So now we just do the pesticide testing at the Water Sciences Laboratory. Students and teachers can access the data stored on a secure online database, and we want to make sure that the owner identity is kept confidential. And we have a bunch of training videos and promotional materials on our website. And this snapshot shows you the recent well owner report for a well that was collected by a group from Norris High School working with the Doane University. You can see that we're really testing for a lot of different contaminants and then comparing those to health benchmark. We published a paper. My graduate student that started out with the Know Your Well program published a paper early last year evaluating youth-led citizen science for improved monitoring of domestic well water quality in Nebraska. This shows a comparison of all of the wells that we sampled, roughly 220 samples, I think, when this came out. Laboratory results showed domestic wells with high nitrate, arsenic, manganese, and uranium. We found traces of atrazine and diethylatrazine, very similar to what was found in that U.S. Geological Survey study. The red bars show the maximum contaminant level, so you can see that a good portion of those wells tested below the MCL, but there's also a significant number that are above the MCL. So if you're interested in the Know Your Well program, here's the website. Really working hard to expand the number of schools. We've had several grants that are supporting this. We're working through a number of Nebraska Natural Resources districts, including the Papio, Missouri NRD, who's been our lead the last 3 years, and as well as the Department of Environment and Energy, who has provided a lot of the funding for this work. I just really am excited about the program. And I hope you are too, now that I've talked about the vulnerability of domestic wells to contamination. So with that, I'll be happy to take any questions from the audience.
Yes, thank you, Dan. If anybody has any questions, they can put them in the chat, and I'm going to go ahead and pull up the poll. If you could take that, we would greatly appreciate it. Okay, Dan, there's a question in the chat that says, are you aware of any programs offered by health insurance companies to financially incentivize rural customers to proactively test their private wells? Seems like insurers have a big financial stake in safe wells.
So health insurance companies, that's what the person is asking about? I'm not aware of any health insurance companies that are promoting water well testing. The closest thing I can think of now is the University of Nebraska Medical Center is sending out posters to doctors and medical clinics that are encouraging patients to have their wells tested if they're on a domestic well. But I don't know of any insurance companies that are doing that.
And then there's another one that says, how can nitrates be reduced in the water?
So are we talking about treatment or prevention?
I'm guessing probably treatment. So they said prevention.
Prevention. Well, there's a number of things that we can do. It's pretty site specific. One thing that I've worked with agronomists and irrigation engineers on is promoting best management practices. So one best management practice may be to only apply fertilizer during the growing season. Now, if you can apply it when the plant is growing, that is actually the best time to apply fertilizer. It's great for the crop, and it's also the time when you are least likely to have nitrate leaching below the root zone. So that's one way. Our sandy soils, because they have such low water holding capacity, another thing we can do is we can irrigate more frequently at lower amounts. So applying just what the plant needs for water is another great practice. If we're able to maybe apply water more frequently and lower amounts, that will also help reduce nitrate leaching. And then I'll get on to the next side. Treatment looks like is in the chat. Typically what people use for treating high nitrate is reverse osmosis. That will reduce nitrate. It does not eliminate it entirely. As long as the system is maintained, it should reduce nitrate concentrations below a maximum contaminant level. We did run into a domestic well during this last round of nitrate testing that concentration was up around 95 milligrams per liter, which is extremely high. Our RO by itself would not have reduced nitrate below MCL using just a straight RO system. Probably the next best method is called ion exchange. They have ion exchange resins that will remove nitrate. Both RO and ion exchange require or can produce a lot of salt in wastewater, and that salt has to be discharged into a wastewater receptacle or septic system. So we could be adding salt to the environment through water treatment. Yeah, I see in the I was going to say, I see in the chat we're talking about don't fertilize if you have high nitrate in your irrigation water. That's exactly right. So if you can account for the nitrate or nitrogen that's added when you irrigate, that's another thing that farmers can do is just make sure that they're accounting for the amount of nitrogen that they're adding when they irrigate. Soil testing is another easy thing that you can do. Make sure that if you have some residual soil nitrate that you're not adding more fertilizer than you need based on what's already there. And then the question is manure better or worse as a fertilizer when it comes to nitrate? That's a great question. Manure is fine. In fact, it can add to the water holding capacity of soil. But if we don't account for that the same way we should account for nitrate in irrigation water or residual soil nitrate, and we fertilize based on what the crop needs, and we're not accounting for the nitrogen that's added in manure, then we're still going to have excess nitrogen in that soil. All right, I see another question is, will household filtration systems reduce nitrate in drinking water? So a simple filter, like a Brita filter, is just for removing particulate. It might have a carbon filter. Carbon in a ceramic filter will not remove nitrate. So you really need something like reverse osmosis or ion exchange, which is a little more sophisticated than like a filter you'd see on the tap.
There's also a couple of questions in the question and answer tab. So David's asking, what has the reception been by doctors to the materials you are sending? Are they actually talking to patients in targeted regions?
I have not heard. We are working with some county health departments. They're super excited about this Know Your Well program, and they hope to connect some well users with well testing through their local high school.
And also, how do you suggest we get more people in rural communities and hotspots to test their water?
Well, that's another reason I like Know Your Well, is because you get high school students excited about groundwater quality. They talk to their neighbors, they talk to their relatives. It's really word of mouth that I found is the best way to encourage people to get their wells tested. I grew up on a farm. I mentioned that at the beginning of my talk, and I know we're suspicious on the farm of anybody telling us what and how to do things. I think it's great when the kids can come up and talk to a neighbor or a relative and say, "Hey, I'm learning about this in my high school science or voc ag class." They're much more likely to get their well tested by one of the kids in the community than they are from a university professor, or even worse is a government agency. So anytime you can get kids excited about groundwater and well testing is good for the community.
Okay, and then one more in the Q&A. Do RO systems remove heavy metals like uranium?
Yes, so, they operate very similar with removing arsenic and uranium. Um, they do not totally eliminate arsenic and uranium, but they will reduce the concentrations if properly maintained.
Okay, and then it looks like somebody asked about grocery stores that have RO systems. Are those effective for removing contaminants?
So that depends. Most grocery stores will be using public water systems as the feed. Uh, as I mentioned at the beginning, the public water systems are required to have their uh, water tested at least once a year for nitrate and a bunch of other contaminants. So what RO does is it just makes relatively safe water even more pure. It really doesn't make it any safer. It might make it a little bit safer, but because you're already getting safe tap water through a public water system, the RO is just to make it lower in dissolved solids content. Now there might
And
be
then
I was going to say there might be a few grocery stores that are on their own well. If they are on their own well, and uh, if they have above a certain number of customers, then they would have to have their well tested annually as part of the Safe Drinking Water Act.
is FFA involved at all with your water testing?
Yes, Know Your Well includes a lot of FFA chapters. We work with the FFA advisor and the VOCAG, the teachers on educating the community and going out and sampling wells. That's a great question.
And then it looks like somebody's asking if 8 to 10 inches of topsoil have been lost since 1900 in Nebraska, would that 10 inches of additional topsoil have been able to prevent nitrates from reaching dangerous levels?
I think it would have helped. You know, that figure of 8 to 10 inches is basically on eroded soil. A lot of that topsoil was probably high in organic matter. and organic matter can increase the water holding capacity of soil. Well, I have to imagine that it would have helped to have some of that higher carbon content soil available to basically keep water in the soil and get the nitrate, the nutrients in the water to the plants.
And then we have, why is the range of E. coli detected? Why does it go from 8 to 34% on the slide that you shared?
Yeah, that is a little bit confusing. The first referred to the number of total coliform hits. If that
And
makes
then
sense.
it looks like the last one is, would hemp be a good rotational crop for reducing nitrates?
It could be. I'm not sure how hemp is grown, what its fertilizer requirements are, or if you'd have to irrigate it. It could be better than, say, a corn soybean rotation. It really depends on the water and fertilizer requirements.
Well, thank you so much, Dan. This was really informative, and yeah, you have a really great program going on for the Know Your Well program. So hopefully that can increase people's ability and to want to test their water so that people know what they're drinking.
Very good. Well, hope everybody has a great evening.
Yes, you too.